Now we can move forward with the IMO model. And basically we got to this stage where I introduced to you this relationship to explain the percentage of the saturated area of the catchment, so the percentage of the area of the catchment that has an infiltration capacity, a potential water storage, lower or equal to a given value C. Okay? So basically this percentage, I say again, of the area of the catchment that has a potential water storage lower or equal to C is given by the relationship that you can see there, which I am writing again here, 1 minus C divided by C max to the power of beta. This is same symbols that you can see there. Perfect. And of course this C is varying from 0 to C max. And you may remember that we made a graph of the progress of FC depending on C. So I have FC here and C on the abscissa. C is varying from 0 to C max. And FC is varying from 0 to 1 because it's a percentage. And therefore, of course, we agree that for C equal to C max, FC must be equal to 1, because again, the percentage of the catchment that has a potential water storage lower or equal to C max is 1. It's the whole catchment that has a potential water storage lower or equal than C max. And therefore, the progress between 0, 0 and C max 1 can be depicted by some examples, which are the linear relationship for beta equal to 1 and a concave curve for beta tending to infinity and a convex curve for beta tending to 0. This is where we got with the last lecture. Okay? Now, let's, from a physical point of view, where are we? We are at the stage such that if we assign a given water storage C, we can derive through this relationship the percentage of the catchment that has a lower water storage. Okay, and from a physical point of view, this is something that we can't really see yet. Okay, we understand. I assign a potential water storage, I give a water storage C, and then I estimate a percentage of catchment with lower water storage. But you know, from the point of view of the rainfall runoff relationship, we still don't see what it means. Now, in order to understand what it means from the point of view, as I said, of the rainfall runoff relationship, now let's suppose that C is given by the precipitation from the beginning of the event. And the cumulative precipitation. And in order to do that, I should emphasize the dependence on T for C as well. So let's now suppose that C depends on T, and let's suppose that it's this potential water storage that is given, let's suppose that it's equal to the precipitation, the cumulative precipitation from the beginning of the event. Again, put your attention on the cumulative term, which means that you start from a time t0, and then it starts raining, so B is the cumulative rainfall depth from time t equal to 0. And this is reasonable, this position that we make is reasonable, because if you think that, as we said, if we neglect evapotranspiration, and we assume that the water storage is given by a tank storage, beneath the soil, indeed, it's reasonable and justified that you equate a given water storage at time t with the precipitation, because think of a tank beneath the soil. So here you have the soil, and you have precipitation here, Pt. And then what happens? It happens that you start accumulating some storage here, and what I say is that the storage is indicated now by Ct, and it's equal to the cumulative precipitation. It works. And of course it works provided you don't reach the maximum storage. Because if you get to saturation, then of course you have the water storage that doesn't increase anymore, but rainfall may still increase. But let's suppose for now that we refer to an area where the soil is not saturated, and therefore this position here is reasonable. Okay, so basically, if you think that the given storage C is now given by the cumulative precipitation, and you enter in this relationship, now what do you get from this relationship? You get the percentage of the catchment area that has a potential water storage that is lower or equal to precipitation. So what happens in this area? It happens that the area is saturated. It cannot store water anymore. Let me repeat. If you equate the given water storage to the precipitation, and then you enter in this relationship here, let's forget about the fact that it doesn't depend on time here. You understand? You fix a time, you compute precipitation, and then you equate precipitation to the water storage, and you get into this relationship. And therefore, what do you get from here? You get the percentage of the catchment, of the area of the catchment, that has a potential water storage that is lower with respect to precipitation, is lower than precipitation. And therefore, if, let me make a graph, and you have this catchment, and you understand that after raining a certain amount of rainfall, cumulative rainfall, and suppose that you see that you have this area that has a potential water storage that is given by, that is lower than precipitation. And of course you cannot locate this area through this relationship. You only estimate a percentage. I put this area in the lower part of the catchment because typically it's the area that gets saturated first. Close to the river, you have the areas that typically, in a typical situation, get saturated first. So what happens in this area? Let me emphasize once again the concept. In this area you have a potential water storage that is lower than the precipitation that you had from the beginning of the event. It means that this area is saturated. It cannot store water anymore. And therefore you can assume that all the rain that rains here is commuted in a river runoff, surface runoff or river discharge. This is something that it's a bit delicate to understand. I want to make sure that you really understood. So if you still don't see what I mean, just let me know. And
So is that what we call the water storage capacity?
The water storage capacity is, let me say, the water storage is equated to rainfall, and you get the percentage of the catchment that has a water storage capacity that is lower than rainfall, and which means that this area where the water storage capacity is lower than rainfall is saturated. It cannot receive, it cannot store water anymore. Because if you have a rainfall of 10, and you get that the percentage of the catchment that has a storage capacity lower than 10 is 0.5, it means that half of the catchment is already full. Okay? And this is meaningful for rainfall runoff modeling, because now you can assume, according to what this model does, that everything that rains on this area is not stored anymore, so it flows downstream through the river, along the river. So if we were able, at each time step, to compute, depending on rainfall, cumulative rainfall, what is the percentage of the area of the catchment that is saturated, then at each time step we can compute the surface runoff as rain times the percentage of the area of the catchment that is saturated. Because, you know, if you get in this situation, so you have a rainfall PT, you understand that you have an area that is saturated. It means that everything that rains over here is surface runoff. And everything that rains here is again storage. So you see a way of modeling, of computing the surface runoff. You still don't know how to do that. But what I really would like to convey to you, the message is, in this way, you see the opportunity, the possibility of computing the surface runoff, because you know the extension of the saturated area, you know rainfall, and therefore you can compute the surface runoff. Now, how can I compute it? And let me redraw this graph larger here. So basically here again FC, and here I can write now PT, and now let's suppose again this is C max, and this is 1. Now this is 0. Let's suppose that the curve is like that, okay? Let's suppose that my curve here is like that. And now, let's suppose that we refer to a given time step dt, okay? Let me indicate it here. And this is a given time step. Of course, what is this? It's a delta p. Okay, but this is occurring at a given time step, t star. So basically, if you focus on this time step t star, let's suppose that you get some rainfall, and I indicate it as delta p, which is a difference in cumulative rainfall, which means it's rainfall falling at time t star. Okay, so what I want to prove now, is that the surface runoff that occurs after rainfall delta P, so the surface runoff that occurs at time t star after rainfall delta P, I want to prove that is equal to this area here. Now let me explain why this is true. First, let me say that this delta P is a depth, is a rainfall depth, so the units are a length. The units are given by a length. Now, what is the value of this area? This area is given by delta P, which is rainfall occurring at time t star, times what? First of all, let's say that this is an infinitesimal increment. So let me say that indeed I can associate a given value of FC star to this time step t star. I can get the average if you want in a finite difference context. But of course you understand that this value is unique because this delta P is tending to 0. Now, you can easily understand that if you multiply delta P times this value Fc star, you get this area. Okay, so you can easily understand that to get this area, to compute this area, you have to multiply delta P times this value Fc star, because you see base of this rectangle times height of the rectangle. Okay, so to get this area from a geometric point of view, it's straightforward. So you have to multiply again delta P T star times Fc star. And how can I say that this area that I computed in this way is equal to the surface runoff at time T star? This is again straightforward. What is Fc star? It's the percentage of the catchment area that is saturated. So it's the percentage of the catchment area that produces the river flow, the river runoff. So basically, if this percentage is equal to 50%, if you multiply rainfall times 50%, you get an estimate of the surface runoff. Of course, it's surface runoff per unit area of the catchment. Okay, so it's if you want to get the volume of the runoff, you have to multiply by the area of the catchment. So if you indicate the area of the catchment as A is area of the catchment, now what is your Q? Your Q at time T star is given by delta P T star times Fc star. Let me delete this sketch here, it's no more necessary. Unfortunately, I have a small blackboard here. So you have delta P T star times Fc star times A divided by the related delta T. Because of course delta T occurs in a time step delta T. So basically, if you refer, for instance, to a time step of 1 day, you consider the rainfall of this day, and then you multiply it by the fraction of the catchment area that is producing the surface runoff, and in order to get the volume, you multiply times by the area of the catchment, and you divide by delta T. So basically, if you believe that this is true, I demonstrated that this area here is proportional to the given river flow.
So, the area Fc times delta P star equal the surface runoff.
I'm sorry, say again.
That is the first one. Fc star times delta P star.
Yeah.
Is equal to the surface runoff.
Is equal to the surface runoff that in terms of depth.
Yeah.
If you want to get the surface runoff in terms of volume, you have to multiply times A, and if you want to get the volume of surface runoff per unit time, which is the river discharge by definition, you have to divide by delta T. I hope this is clear. Yeah. So basically, now let's suppose that first of all, before moving forward, you understand the meaning of the area below the curve given by this relationship here, and you already understand that probably we will need to compute the integral of this relationship, because the area is given by the integral of this relationship here. So you understand that if you want to compute the volume of water that from time zero flows in the river, so the volume of surface runoff, this is rightly given by the area below the curve. So let me redraw the curve now. And let's suppose that we now want to refer to a time step t at, okay? And I want to compute, let me redraw the curve first, fc. 0, 1, and here we have C max, and this is PT. This is our curve. So let's suppose that now our question is at time t at, I want to compute the volume of surface runoff. The volume. And first of all, what should I do? First of all, I should identify at time t at what is the cumulative rainfall value. And then let me indicate here on this curve the cumulative rainfall value P at. Okay, then I need to compute the integral between 0 and P at of this curve. This is the volume of surface runoff. Please pay attention and recognize the difference between computing the river flow at a given time step and computing the volume from the beginning of the event of the surface runoff. These are two different things. Okay? Remember that the river flow is defined as the volume of water that passes through a given river cross-section in unit time. The cumulative volume of river discharge, river runoff, is basically the integral of the river flow, and it's given in this case by the integral from 0 to P hat, where P hat is rainfall at time T hat, the integral of this relationship. This is the logical conclusion of what we said so far. Now, of course, I understand that this is a model that is not straightforward to understand, and I think that this makes the model interesting, because you will see that the model is very simple, but still, the elaboration that was done, the concept that was elaborated is quite complicated, and at the end of the story, because the concept is a bit complicated, it's also very detailed, but at the end of the story, it's expressed in simple mathematical terms. And this makes this model interesting. So now, if we accept this interpretation that I provided to you, and I say again that the integral of this curve gives us the cumulative volume of runoff at the given river cross-section, now what we have to do in order to compute the cumulative runoff, of course we need to compute this integral. And be careful, given this relationship between the cumulative runoff and the river flow, once that you know the cumulative runoff, you know the river flow, because the derivative of the cumulative runoff, it's the river flow. So once that you define this cumulative runoff, which means that, for instance, after the first hour, you know that 1,000 cubic meters per second passed through the cross-river section, and if you know that at the end of the second hour, you have 2,000, the river flow between time 1 hour and time 2 hours is 2,000 minus 1,000 divided by the number of seconds in 1 hour, which is 3,600. So once that you know the cumulative runoff, the delta cumulative runoff over dt is your river flow. So once that you solve this integral, then you are done with the application of your rainfall and off model. Okay, so let's see how this integral can be computed. And basically, I want to draw your attention on this sketch, because you can understand only so far the first part of it. You see, what you see here is a representation which is analogous to this one, or that one, where you see the percentage FC in the abscissa and not in the ordinates. And in the ordinates, you see C, the storage. And also, there is a complication here that is varying from 0 on the right to 1 on the left. And it is done in this way, because in this way, you can better see it as a tank. This is like a tank where you don't have an horizontal limiting height. You have a limiting height of the tank, so a limiting storage, which is given by this card, which has this relationship here or there. So they used this sketch because it makes it more similar to a tank. But I prefer to use at the beginning this sketch because it allows me to better explain why the integral of this relationship gives the surface runoff. And now, the integral would be given by this area here. If you think at our relationship there, what I depicted with, what the area that I highlighted, the integral is given by this piece here. I just wanted to explain to you why they are using this relationship. And here in the next ones, you see the computation of the integral. But let me wait before showing the slides, okay? Now let's compute the integral then. So what is the integral that we have to compute? So basically, I have to compute the integral between 0 and pt. Let me indicate t as a generic time, or you can also, let's put t star, in order to emphasize that it's a given time, not a generic one. So, and therefore, I have to compute the integral of 1 minus c divided c max to the power of beta in the c, where c is the variable of integration. This is the integral that I have to compute between the extremes 0 and p t star, which basically means that I am computing the integral between time t equal to 0 to time t equal to t star. But I need here to compute the integral in terms of, I need to give the extremes in terms of rainfall. Of course, rainfall is occurring at a given time t. And when you have your data, it's immediate for you to associate at each time the given rainfall. Now I need to compute this integral then. And look, the computation of this integral is very straightforward, but it's very easy to make mistakes, so we have to be very careful. We can incorporate this integral in two integrals, so I can write it as the sum of the integral between 0 and pt star of dc minus the second integral between 0 and p star of 1 minus c divided c max to the power of beta in dc. And keep in mind that this P is cumulative rainfall, okay? Okay, let's move forward. The first integral is straightforward. The first one can be written as C, computed between the extreme pt and 0, minus. Now let's compute the second integral. And the second integral, I say minus the result of the integration is, and I will discuss this later, let me write it down first, C max divided beta plus 1, which multiplies 1 minus C divided C max to the power of beta plus 1 between the extremes P, T star, and 0. And also I need a minus sign here. And now let me discuss with you why this is the result. So I prefer to prove that this is the correct result of the integral by computing the derivative of this relationship and checking if the derivative of this relationship between squares is, gives back the value 1 minus C divided by C max to the power of beta. So what is the derivative of this piece here? First of all, it's the derivative of an exponent. So if you want to compute the derivative of this, we should write that is equal to beta plus 1, which is the exponent, times C max minus, I put the minus here, divided beta plus 1, which multiplies the argument of the exponent 1 C divided C max to the power of beta, because it's beta plus 1 minus 1, times the derivative of the quantity that is elevated to the exponent, and this derivative is times, I write here, minus 1 over C max. So this is my derivative. And then, if I simplify, I see that here, the minus goes away with the minus, the beta plus 1 goes away with the beta plus 1, and here, C max goes away with C max. So it's perfect, and yes, it's perfect. So this is the result. The result is correct. Here I just computed the derivative and checked that everything gives back the original quantity that I integrated. Okay, so I am happy now with this integration, and I can move forward by computing the results at the extremes of the interval of integration. Let me just now delete the derivative that I computed. And let me say that we can change the sign here, the signs. And basically what we obtain is equal to, this is Pt minus P0. P0 is 0 because its commutative manifold at time 0 at the beginning of the event is 0. So this is Pt minus, plus, sorry, C max divided by beta plus 1, which multiplies 1 minus Pt, Pt star, sorry, I forgot some stars here. Yeah. So 1 P star divided C max, beta plus 1, minus C max divided beta plus 1. So this is my result. And let me better explain. I think for the first term it's easy, it's straightforward. For the second term, let me compute the result of this expression between parentheses for C equal to B star, and I just obtain the same relationship with P star substituted for C. And then I put the minus because it's the second extreme. If I put a 0 here, I have 1 to the power of beta plus 1, which is 1 multiplied by C max divided by beta plus 1, which is what I find here. So this is our surface runoff. You may see one thing. You may see one thing here. Just let's see if it makes sense. Okay. So basically, I said at the beginning, if you remember, that I equated rainfall to the given C value at time t star. You may remember that I said, let's suppose that C, water storage, the given water storage, is equal to rainfall. And I said, I can make this assumption because I neglected evapotranspiration. And I said, I can make this assumption as long as P is lower than C max. Because I said, of course, when everything is saturated, I cannot say that the water storage is equal to rainfall. The water storage, once that the basin gets to saturation, is fixed, is the same, remains the same, even if it continues raining. So I said this substitution makes sense, provided that you neglect evapotranspiration, and provided that you have a rainfall, a cumulative rainfall that is still lower than C max. Okay, that's fine. Now, let's see, what is the volume of cumulative runoff? It's given by rainfall from the beginning of the event. And in your mind, you understand that then we should subtract something at this stage, because rainfall is whatever it's rainfall gives to you the volume that fell over the catchment, but something